So in this chapter, we're going to talk about probability distributions. Let's go back and talk a little bit about Chapter 2 for a second. Do you remember what a frequency distribution is? Okay. It's where you have all the outcomes listed, all the different possibilities listed, all the data values listed, and the frequency of each one of those data values. It's a table, it's a summary. How do you turn a frequency distribution into a relative frequency distribution? What's the difference between relative frequency and frequency?
Percentage.
Okay, you're turning it into percentages, so you don't say how many had this value, but it was what percent of the total had this value. Percentages and probabilities are the same thing. So a relative frequency distribution for a population, or an estimate of a relative frequency distribution, an estimate of a probability distribution contrived from a large enough sample that can be inferred to apply to a population, is a probability distribution. So probability and relative frequency are essentially the same thing. It's just the way that we look at their meanings. So first of all, a random variable is a quantitative variable that assumes a value determined by chance or random outcome. Okay? That's what a random variable is. A random variable is discrete if the number of possible outcomes is finite or countable. Discrete random variables are determined by a count. If you could,
that implies it's an integer?
Except for money, yes. Okay? That's a good definition. In fact, my way of defining discrete is if the only thing you need to quantify the values is two hands and one brain, when you can count it, then it's discrete. If you can pick it up and set it down, it's discrete. I can count the number of pencils in my cup. 1, 2, 3, 4, 5. Okay?
But if you look at money as pennies instead of dollars, then
Exactly. I can count my money because I'm basically, our money system is based on, it's base 10, but it's in hundreds. So a penny is 1/100th of a dollar, and if you talk about dollars and cents, then there's nothing between $1.11 and $1.12. Okay? So it's discrete in that sense. Being discrete does not preclude decimals, except that the decimals have to be able to be narrowed down to a point where there isn't anything between one and the next one. Okay? Which is, money is the best example I can think of. If you require something other than these and this to quantify the random variable, I don't care what it is. If it's a thermometer, if it's a measuring cup, if it's a yardstick, if it's a ruler, don't care. If you need some kind of device to quantify what you're measuring, it becomes continuous. Their definition of continuous is if it can take on any value in an interval, possible outcomes cannot be listed. Continuous random variables are determined by a measure. Measure implies measuring device, not these. Measuring device. Ruler, scale, thermometer, odometer on your car. Okay? Measuring device of some sort. Then it becomes continuous. That's the only way you need to remember to distinguish between discrete, which is counts, 1, 2, 3, 4, 5, and measures. They require a measuring device. Okay? Quick quiz. X represents the number of players on a basketball team. Is that discrete or continuous?
Discrete.
Because
You can count the players.
you can count how many players. Excellent. X represents the length of time it takes to swim 4 laps in a pool.
Continuous.
Continuous, because what do you need to measure the time?
A stopwatch.
A stopwatch. X represents the number of daffodils planted in a garden. Discrete. You can count them. 1, 2, 3, 4, 5. X represents the height of 7th graders. Continuous. You need a yardstick, meter stick, tape measure, something. Now we're going to define a probability distribution. Basically what a probability distribution does is it assigns a probability to a random variable. The random variable can be discrete or it may be continuous. In Chapter 5, for the most part, we are going to talk only about discrete probability distributions. So all of our random variables in Chapter 5 will be discrete random variables. In Chapter 6, we will move to continuous random variables. A probability distribution is a description, like a frequency distribution, that gives the probability, rather than the count, for each value of the random variable, and it's often expressed in the format of either a graph, a table, or it can be expressed in the format of a formula. Now, for discrete probability distributions, we generally don't use a formula. For continuous probability distributions, we do. Graphs and tables can be used for discrete or continuous, either one. These are 2 requirements for a probability distribution. These actually come straight out of Chapter 4. The sum of all the probabilities in a probability distribution must equal 1. The sum of all the relative frequencies must equal relative frequencies
100%.
100%, because when you get to the bottom of that list, you've counted all or 100% of your data values. Same thing with probabilities. Probability has to total up to 100%. If it only totals up to 75%, something strange was going on. Okay, so if you total up the probability column in a probability distribution and it doesn't come up to be very, 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 very close to 1, as in no more than 1/1000th away from 1, then there's something wrong with that probability distribution. It's not legit. The other requirement is that probabilities must all be between 0 and 1. Now what that basically says is you don't have negative probabilities. There is not a negative 12% chance it's going to rain tomorrow. Okay? There's either a 0% chance or a 100% chance or somewhere in between, but not negative probability. And the fact that it has to be equal to or less than 1 tells you that any one probability cannot be more than 100%. The probabilities always have to be between either not possible at all or the only possibility. This is an example. This probability distribution is given as 1, but is it? First question you ask yourself, do all the probabilities add up to 1?
No.
No. 0.10 plus 0.20 is 0.30, plus 0.30 is 0.60, plus 0.20 is 0.80, plus another 10 is 0.90. So no, it doesn't add up to 1. So no, this is not a probability distribution. Just because of that, the probabilities don't add up to 1. Okay? Is this a probability distribution?
Who knows?
Now, this one takes a little longer.
No,
Because,
it's greater than 1.
okay. And it is because if you add up the probability column, it will be greater than 1. Okay? Now, what if this had one of the x values to be negative? Is it assuming that the probability column does add up to 1, would it not be a discrete probability distribution if one of the x values was negative?
Probably not, because that one would be an invalid probability.
Not necessarily. Let's talk about that. What would a negative value in your random variable mean? Okay, let's talk about gambling. You play roulette, okay? There's a lot of different possibilities on roulette. Can you win at roulette?
Well, it depends what your definition of winning is.
Well, on any one given round.
Okay.
One given play, yeah, you can win. And if you win, do you get some money? Yeah. Okay. Can you not win but not lose? Can you not
Can you
get
break
any money?
even?
Can you break even?
Sure.
Yeah. Neither you nor the house could win. Okay? That's a possibility. So your value there would be you don't get any money, so that value of your money is 0. But if you get some money, it's positive. What if you lose? Can you lose at roulette?
Mm-hmm.
What happens when you lose at roulette?
Your money goes bye-bye.
Your money goes bye-bye. You lost your money. Your value for that particular round is negative. So your random variable could be negative.
If you're looking at amount that you've won,
Yes. You're looking at the amount that you won. X represents how much did you win. Okay? And we'll come back to that example later. But that's a common misconception that the X can't be negative. It can. Probabilities can't be, but the X can be.
oh, I see.
Okay? Now, if you want to find the mean and standard deviation of a probability distribution, the mean is given the symbol mu, and it is referred to as the expected value. It's also called the expectation. Basically, if you had to look at a situation and decide what you thought would probably happen, what had the greatest likelihood of happening, that would be the expected value.
Which is why that's applied to a population as opposed to a sample.
Exactly. That is why this applies to a population rather than a sample. Okay? Basically, what you could think of the expected value being is the long run average. Okay? Think about tossing that coin. In the long run, we expected heads half the time, tails half the time. Okay? Without putting a number on it. There is a formula for it. This is the formula. You add up the sum of the product of X times its probability. It's kind of like a weighted mean. It's essentially the same as the weighted mean when we're doing your grades. If you want to find the mean and standard deviation of a probability distribution, the easiest way to do it is to use your calculator. Your steps are listed there on your handout for putting it in your calculator. If you want to find it only the mean, then you can multiply x times p of x and add it up, which is what's being done here. But this is the much easier way to do it. So we're going to actually go through the calculator steps here right quick. And then we're going to stop here because this is a convenient place to stop. So you hit your stat button, which is what you always do when you're going to do a statistics problem. You always hit your stat button. We're going to hit enter to edit, and I'm going to use list 1 and list 2. And on the PowerPoint, I'm going to move back to just the probability distribution. And we're going to enter the probability distribution in by putting the X's in list 1, 0, 1, 2, 3, 4, 5. And then the probabilities will go in list 2. And when you enter in 0.0005, it will change that to 5e-4. Okay? Because it can't show you more than a certain number of characters. And then 0.0091 will actually fit, which tells me that 0.0005 should have fit. And then 1.8 needs to be changed to 0.0648. And then 0.2297, 0.4072, and 0.2887. So you enter your probability distribution in list 1 and list 2 as it says. Step 1 says stat, enter, edit, enter the X values in list 1 and the PX values into list 2. And then the next step says press stat again, go over to calc, choose one variable statistics because we're only looking at one discrete variable here, and press enter. And then tell it that you want to use list 1 as the X's and list 2 as the probabilities. And it comes back and it tells you that the mean of the distribution is 3.9001 or 3.9. Standard deviation of the probability distribution is 0.926. Notice that there is no sample standard deviation. And that's because probability distributions are a population. Okay? What this basically tells us is about 2/3 of the time we're going to get a number between 3 and 5. If you want to round everything off. The reason 3.9 is likely the likelier the expected outcome is because if you look at the table, what has the highest probability?
4.
The value of 4, which is really close to 3.9. But 3 and 5 also have somewhat higher probabilities than any of the other values, which explains your standard deviation. Okay? And we're going to stop there. We will pick up with some practice when we come back next time. And just to let you know in advance, number 1, we will have a quiz over chapter 4 at the beginning of class next time. And class will start promptly next time. And I'll tell you why I know that for sure. I'm not going to be here. But my sub will be. We will have class, you will have the quiz, and she will have an assignment for you. Okay? So be sure to show up next time.